So, as announced already via my courses, we now fixed some details about the student projects. As you know, the student projects give you up the opportunity to collect up to 40 points. So whatever we do, rescaling, in the end, you get maximum 40 points for the student project. And just to remind you, in total, we award up to 100 points in this course via different activities, such as the My Course quizzes. And the student project gives you up to 40 points. So it's quite a substantial part of the total number of points. And we will use peer grading, similar to the first assignment, but we will change a bit the modus. Particularly, we make it double blind. So in this first assignment, which you all have now, or most of you have completed, you knew the identity of the student whose submission you reviewed. So the students, you didn't know who were the reviewers of your submission, but I think, as I understood, you know, or you were informed about the name of the student who you are reviewing. And in this machine learning project, when we do this peer grading of the project reports, we will make it double blind. So neither the reviewers know who they review, nor you know who reviews you. So let's do it double blind then. The submission deadline will be end of March. So the tentative submission deadline is Sunday, the 28th of March, which should give you plenty of time to work out your machine learning problem and try out different methods. I have here put here a link for some advice on good writing. Maybe some of you already are about to start writing a bachelor thesis or a master thesis or some assignments, some seminar work or seminar report. And you could use this project here, this course project, to try out ideas for your thesis. So in this project, you will, or in this machine learning project, you will get up to 5 reviews from your peers, which is quite valuable. So it's not easy always to get to get feedback. And here you can get up to 5 feedbacks in the form of peer reviews. There's already one question. So you shouldn't include your name, student number and such in the project report. Yes, we didn't write it yet. That's a good point. So I will add this here for the criteria. You should not indicate your identity in the report. So without author name, of course. Otherwise, yeah, we will have a pre-screening stage most likely, where our teaching assistants reject or push back such reports which include names, and you have then to remove the name and submit it again. But we should make this more clear right from the beginning to save a lot of extra work. Yeah, I had a question, some questions recently. If a student has already a related project, for example, in some seminar course, he or she looked at certain machine learning methods, and can a student reuse the text from there? And in general, it's not possible to use the same kind of performance or the same output of you, the output of your thinking, which is a report or an essay. You cannot use to get more than one attainments, which should also be clear by common sense. So you can refer in your reports to the other submissions, but you should not copy paste text that you submitted already for some other thesis, and vice versa. So if you develop here an idea that you then want to continue and work out for a master thesis, then you cannot copy paste. I would not copy paste the report that you submit here, but rather take into account the feedback that you got here from the peers and further develop it, and also refer. You can refer then in your thesis that you have a preliminary version of the thesis was used as a student project in this course. So you must always indicate the sources of information, and also the source can be your own previous work. That's also important. It's not only that you must indicate the work of somebody else, but also your own previous work when you use them as a source. Okay, then document formatting. This is inspired by the ICASP. So in order to give you a bit of motivation, this is typically what you are starting out when you write a conference paper. So there's a nice conference coming up. Hopefully it will be live in person in Toronto, in Canada. And they specify how many pages. So we also use maximum 5 pages with up to 4 pages technical content. And the 5th page can only contain references. So there you list the other works or sources of that you used for your report. A list of references. Then we use font size no smaller than 11 points, and we use a single column format. So in this conference, when you use the templates, they are in double column, but we will use single column. Yeah, the document must be as a PDF in PDF form and maximum file size 1 megabyte. Yeah, and the required language is English. I can only provide service in English, and so are TAs, or most of our TAs. Okay, then we also specify the outline of the project report. So you have to follow this section list and also the titles of the sections. So there's no need to think about how you structure the report. We tell you already how to structure the report. So there are 5 sections. Okay, just briefly going over, just went briefly over the specifications for the project, and you have plenty of opportunities to ask in case of further questions. So in the exercise sessions, for example, we have 6 parallel exercise sessions each week where you can stop by and ask directly our teaching assistants, and by email, please ask, and also use the discussion forum or SULIP discussion forum. Okay, so let me now start with the actual lecture content. Today, I want to talk about model validation, selection, and regularization. Yeah, that's a good point. So I will give the stage to my co-lecturer, Professor Sick, who will briefly introduce the schedule of the next lectures. So let me just find you. Stefan here. Promote the panelist. Yes, please, Stefan.
Okay, now it works, I think. Yeah, thank you, Alex. So I just wanted to briefly say a few words about the second round. So we had originally planned, as you might have noticed, to start the second round today with a lecture on regression. But in discussion with Alex, it turns out that it's actually better, especially for the project, when we have some content on the model validation, selection, and regularization first. So that's why we have this reshuffling. And so today's lecture will be by Alex, and I also wanted to introduce that. So effectively, the regression lecture will start next week, Monday, and before that, on this week on Wednesday, my PhD students, Sue will also have one part. So she will give this will be a practical session on machine learning with Python. So be prepared to be interactive during the session and also ask a lot of questions. So there will be, basically this practical interactive session on Wednesday, and then on next Monday we start with the regression part, and that's not a problem at all. So we can flexibly change the lecture content. So there's nothing which is missed. We basically just shifted the original plan now by one lecture to by one lecture, and instead took one of the later lectures now for today. Yeah, that's actually all I wanted to say.
Thanks a lot, Stefan. Yeah, I see here one more question regarding the first assignment. So you didn't receive a clear, explicit review on your project statement or on the machine learning formulation. I'm not sure if this is by default that you get an overview of your grades. I need to check with the TAs. So you can always look up your current grades in the grade book in My Courses. So there's something called My Courses grade book. If you cannot find it, please reach out to the TAs in the exercise sessions or write us an email. But you can see there, you should see the results of the peer grading. Yeah, you should also get access, I think, to the individual reviews that you got, to the peer reviews. Yeah, please, if you have problems seeing that, please ask the TAs. Okay, yeah, another comment that you cannot see the reviews. Yeah, I need to check this. Maybe we need to enable this by the My Courses activity. I will have a look at that. Yes, you should get the peer reviews, definitely. Okay. Let me now continue with a few slides, and then after the slides, I want to give a quick demo or walkthrough in a Python notebook. Okay, so just as a disclaimer, whenever I talk about a model in this course, I mean a hypothesis space. Yeah, and first of all, or as a reminder, what are three main components of machine learning that we have talked about the last 2 weeks? Data, model, and loss. Very good. First, data. So data is a set of small units of information, which we call data points. Each data point has certain properties. Some of them we call features. Features are those properties we can measure easily. And then another type of property is some high-level fact or quantity of interest, which we call label. For example, one of my favorite examples now, very timely now also because we have snow. So a data point is some ski day, and the feature might be the morning temperature. We can measure this easily in the morning, but what we're interested in, the quantity of interest, is the maximum daytime temperature. So, and in order to learn a hypothesis, so machine learning is about learning a hypothesis that reads in the feature X and produces an estimate or a good approximation of the label. So in order to do this, we need several data points. So a data set or data is just more or several data points. And typically, the more data points we have, the better. Yeah, one important parameter or key figure of a data set is the sample size, the number of data points, in particular, the number of data points for which we know the label. So if data is considered the fuel of machine learning, then it's the raw oil. And the labeled data points is then the high performance, high-end fuel that you use for your engines. So we would like to have labeled data points. The labeled data points are really this is the gold in the data. Yeah, here's one example with 4 data points. So these 4 data points are obtained, for example, by the Finnish Meteorological Institute. For each data point, we know the feature, the minimum temperature, and the maximum temperature. So far, so good. So this is data. Yeah, what do we do with data? Data per se is useless. We always need some model or a hypothesis for the data or for the data generating process. So in this course, I mainly use the term hypothesis for a map, a function that reads in the feature as an argument X and outputs some number that we interpret or that we use as a prediction for the label. That's why we call it Y hat. So it's an estimate of the true label Y. Yeah, and machine learning only becomes interesting if we have more than one hypothesis, because if we only have one hypothesis, then we can only use it. And an example is this song identification app, Shazam. I think now there's not much learning going on anymore in the Shazam app, or not continuously, but what you do on your app, you just run a function that reads in the features of a song in the case of Shazam. So it's called Shazam. And it outputs a guess for the song title. So the Shazam app mostly does nothing but evaluating a function, and this can already be challenging. So if there's a function is very complicated, then evaluating a function might already be a challenge. This is also called inference in machine learning. Whenever you hear machine learning inference, then this means just evaluate a hypothesis map in order to compute a prediction. This is inference. But what we in this course are mostly interested in is how do we learn a good hypothesis? And we, as I said, machine learning only makes sense if we have more than one hypothesis. Otherwise, there's nothing to learn. And one of the simplest spaces or hypothesis spaces or sets of such hypotheses is a linear function. Linear functions we have quite good grip on. We know more or less their properties, their statistical properties. So this is a good first choice, a linear function. But why not using degree 3 polynomials or degree 10 or degree 100 polynomials? So typically we have many different options for these hypothesis spaces or models, and each particular model corresponds to one machine learning method, like decision trees uses one particular hypothesis space, deep learning uses another construction of a hypothesis space, polynomial regression, another construction of a hypothesis space. So which one to use? And for this we need validation. So let me explain what validation is. Oh yeah, first of all, if we for some reason we know what a good model is, or we know what a good hypothesis space is, then first we have to measure the quality of a hypothesis within a hypothesis space. And for this, we need a loss function. So a loss function is a measure, in some sense, a measure stick or a scale that tells us how good is one particular hypothesis. And some popular loss functions are discussed in my lecture notes. For example, the squared error loss. So for each data point, we compute the predicted label. So it's this here for this data point. This is the predicted label, but the true label is here on the y-axis. So there's a difference. This is a prediction error. And the squared error loss uses the square of this prediction error to measure the quality of a hypothesis. So, and what machine learning or many machine learning methods do is then solve an optimization problem. They solve the optimization problem of finding the hypothesis out of the hypothesis space, which has the smallest average loss on the training set. This average loss on the training set we also call training error. Okay, and then what happens nowadays, because we have so powerful hypothesis spaces, we have such large hypothesis spaces like artificial neural networks. They involve billions of parameters, and these artificial neural networks, or these deep networks, they represent extremely high dimensional hypothesis spaces. But you don't need to look to deep learning. You also see this effect for polynomial regression. So if we use as hypothesis polynomials, and if we allow for a very large degree, then it turns out when you have a very large hypothesis space, you can easily fit perfectly fit the training data. So it's not really a challenge to make the training error small. So for example, for a linear predictor, we get some large training error. So here we see with this linear curve, no matter how we position it, we will incur some error, some significant error. However, when we look already at degree 3 polynomials, then we almost perfectly can fit these data points. So we get training error close to 0. So if we use larger degrees, we get the training error pretty soon towards 0. And this is not what we want. So because overfitting might happen. Overfitting means that we overfit the training data. So we focus too much on fitting the training data, which we can do easily just by, in some sense, by memorizing the training data. We just pick a function, they perfectly go through the training data. And if we use a large enough hypothesis space, we will for sure find such a function, because there are simply so many functions in a big hypothesis space that just by pure luck, we will find one that perfectly goes through the training data points. But such a function might not be any good on a new data point. And this is what we really care about. We don't care about how good is the predictor on the training set. We care about how good is the predictor on a new data point. For example, when the predictor is used to predict the maximum daytime temperature, then I don't care how good it is on old FMI data, but I care how good is this predictor today. This is the new data point. And here, if we overfit, then this predictor might not be any good on other data, which is different from the training data. So this is referred to as overfitting. And this is one of the key challenges in machine learning, to not get yourself fooled by overfitting. So whenever you start applying machine learning and you choose a model like polynomial regression and you train it on some training data and you get the training error 0, so this is just a good warm-up exercise, but it doesn't mean much. You always have to try out your predictor on data points which are different from your training data set. And this is exactly what is validation. So validation means try out the hypothesis that you learned on a training set on some other data points which are different from the training set. Yeah. Just before I talk more about validation, you can easily show using elementary calculus knowledge that, for example, if you have m data points, like if you have 2 data points, m equal 2, if you use a degree, a polynomial with degree, maximum degree n-1, you can perfectly fit any m data points using such a polynomial as soon as n is not smaller than m. So, and this tells you that in order to avoid overfitting or to get any meaningful result using polynomials of degree n-1, you need to use at least n training data points. So this m is the size of your training set. And you want to avoid this condition, because under this condition, you can perfectly fit any training data set. And this means you will overfit. So in order to avoid this bad condition, you must make the sample size sufficiently large. So you must, if you have a degree of 100, or n-1 is 99, so this means you need to have at least 100 data points to reliably train a polynomial regression method. And in practice, it's even better to have 10 times more. So to be 10 times, to be away from this condition by a factor 10. So if you use degree 100, then it would be good to have 1,000 data points. And this n, which could be interpreted as the number of equivalent features of a data point used by a linear regression model, this n might be billions for modern machine learning methods. Like this n might represent the number of tunable weights in a deep neural network, and they have billions of tunable weights. So this condition here tells you that if you use one of these super powerful deep neural networks, you need to have 10 times more than billions of training data points. For example, if you want to use deep learning to detect if an image shows a cat or not, then you need 10 times more than billions of images for which you know if there's a cat or not. Okay, yeah, here, this is an illustration of this condition. So if you have n equal 2, which means maximum polynomial degree 1, and 2 data points, then for any, so each color corresponds to one particular data set. So here's one data set of 2 data points. Here's another data set of 2 data points. Here's yet another data set of 2 data points. And for any such data set of m equal 2 data points, you will always find a hypothesis that perfectly goes through it, passes through it, and makes 0 training error. Okay, so the big idea now is to do validation. And how do we do validation? Well, we split the data points that we have. So in this case, we have 4 data points. For example, 4 previous days that we download from the Finnish Meteorological Institute. And then what we do is we split it into a training set and a validation set. we use the training set to learn the hypothesis, for example, by minimizing the average squared error. And then after we learn the hypothesis on the training set, we just apply it on the validation set and diagnose the method. So here I have illustrated a simple example by using a linear hypothesis. So we use the errors, these errors we use to optimize the weights of this linear predictor, like the offset or the slope. This is tuned using this data set here, this training data set. And then after we train, we are finished with the training, we try it out on the validation set. And then looking at the validation set often allows us to identify overfitting. So for example here, like this degree 3 polynomial, which I showed before, perfectly fits the training data, but we immediately see that it overfits because the validation error is large. Yeah, so this is maybe the most important picture for the practice of machine learning. So you have two bars or some visualizations of two quantities, the training error and the validation error. And you diagnose machine learning in 90% of the time when you do machine learning in practice consists of comparing training with validation error, and based on this comparison, decide what to do. Should you collect more training data? Should you use more features of the data point? Should you use a decision tree instead of a linear regression? All of these decisions can be based just by comparing these two numbers, the training error and the validation error. And this is what I really want to see in your machine learning project reports. I want to see such a plot, training error and validation error. At least one such plot. Yeah, so there are now several questions, which is good because this slows me down. So there's one question. After validating the model, can we then train with the entire data set? So you use validation then. So first of all, you use validation to spot overfitting. So here on the right, we see a scenario where the training error, this blue bar is very small, but the orange bar is very large. So this means overfitting. And this means that degree 3 polynomials are not a good choice. And then in the next step, you can use this information to select between different models. So this I will talk about in a second. So then you can also look at the validation error for model 1, which is smaller. And you use then the validation error to choose the model. And after you have chosen the model, you might retrain it on the entire data set. But there are mixed opinions about this practice. I would say, just to be on the safe side, in the end, you should always look at the third data set, which is called the test set, which I will talk about later. But what you do before is kind of not always clear case. So it might be a good idea then, after you choose the model, to retrain it on the entire data set. Yes. Okay, there's another comment. So we should find a way to find the best balance according to training data points with the label or the next missing data point. Yeah, so as I understood the question, if I understood the question right, so you want to balance this training and validation error. So what you typically do not want is the training error is much smaller than the validation error. And you will learn different techniques like regularization or model selection techniques in this course that allows you to bring down. So what machine learning in practice is then about, try out different methods to bring down the validation error, even at the expense of increasing a bit the training error. And at some point they meet. At some point there's the sweet spot where they meet. And then you hopefully, what you get, this error here is acceptable. And if this error here is acceptable, for example, you have a target accuracy. You want to find the cat images with 99% accuracy, or you want to make the detection error smaller than 1%. And if this here is 1%, then this figure, then you're done. Then you have solved the problem. But in general, to start with, you will typically get a very small training error, but a large validation error, and then you want to balance those two. There's another question. In general, what percentage of data is better to be selected for validation? So this question addresses the choice of the split ratio. So here I choose 3 data points for training and 1 data point for validation. And the question is, wouldn't it be better to use 2 data points for validation and 2 for training? And I have to say, there is no clear-cut answer for this. So there is no widely applicable rule or formula that tells you the optimal split ratio between validation and training. This depends highly on statistical properties of your data set. I will touch this a bit in more detail in round 4 of our course later on. Okay, then another question. Is it unusual to have smaller validation error than training error? Yeah, that's a very good question. So if the validation error is smaller than the training error, then this is a rather extraordinary case. And this might point to a wrong implementation of the training algorithm, because the training error is what you get on the data set on which you optimize your hypothesis. And it's somewhat unlikely that this error could ever be larger than the validation error that you then get on other data sets. It might be possible that you have pathological cases. Actually, that would be a good quiz question. If it could happen that you train properly, but the validation error is smaller than the training error. In general, this cannot happen, and this should not happen, let's say. And this would point at a wrong implementation of the machine learning algorithm. For example, there are certain parameters in the training algorithm, like a step size when you use gradient-based methods. So gradient-based methods are discussed in chapter 5 of my lecture books. And there are some parameters like a step size. And when this step size is chosen too large, for example, then the training doesn't work. It will never find the optimal hypothesis. And then you might end up with a training error that is larger than the validation error. So if the training error is larger than the validation error, this might be an indicator that something in the training algorithm is wrong. Yeah, that was also a very good question. Let me see, what other questions do we have? How to select training sets, how to select validation sets, any rules? In general, we just randomly select subsets. So you randomly divide the data set that you have into 2 subsets. One is used as the validation set and the other as training set. But of course, it might happen that you are very unlucky, in particular, if you have small data sets, that for some reason, the split is very untypical. So the validation set is a very, might be an outlier, for example. So it might not be representative for the whole data set. And then you might have an atypical behavior, let's say, of the training error. And to average this out, there's a slightly more fancy version of the simple validation method, which is called k-fold cross-validation. And this amounts just repeat the validation step k times. K is a parameter. For example, k equal 5 is one popular choice. And no, I don't know a general formula for the optimal value of k also in this case. So this is often also trial and error. So you use different splits. So in each iteration, you use a different subset as the validation set and the rest as training set. And then you average the resulting training errors and validation errors over all these repetitions or folds. These are called folds for some reason. So this should avoid, or this should average out some unlucky splits, some very unlucky splits where the validation set would be really not representative of the entire data set. Yeah. Yeah, one comment. In K-fold, do you change the training set each time as well, or just the validation set? Yes, because as soon as you change the validation set, you must also change the training set, because the training set is the complement of the validation set. Yes, so you change training and validation set in each fold. Another question, how many data points are required for validation? Yeah, there is no general rule. In general, you want what you use the validation set for, or what you use the validation error for, is an estimate or approximation of the average error that you get when you average all the prediction errors over all possible data points. In practice, you cannot do that, but what you could do is you could assume a probabilistic model, and then you can define a quantity called the risk, which is the expectation of the error. And the validation error serves as an estimate of this expectation. And then you can use tools from probability theory, which tells you how many data points do you need in the validation set, such that this estimate is within a certain percentage with 99% probability. So you get this confidence intervals. But these confidence intervals you can do only when you know a probabilistic model of the data set, and you need to estimate this probabilistic model. So it is possible, but it might not be really practical to get such formulas. But I have to say, this sounds like a good idea for a quiz question for round 4. Okay, how many data points are required for validation? I just discussed this. Yeah, so for this problem, when we look at this here, we have two models. Model 1, linear predictors. We got the training error and validation error. Then we did the same for model 2, degree 3 polynomial. So which one would you pick? Which model would you use? Model 1 or model 2? Model 1, yes, because the validation error is smaller. Yes, so you got already the idea of model selection. So you choose the model based on the smallest validation error. And we can interpret this validation error as the loss, something like a loss for a hypothesis space. So the loss which we used so far was used to measure the quality of an individual predictor or a hypothesis. So we used the loss to evaluate the quality of a single hypothesis. And the validation error is used to evaluate the quality of a whole hypothesis space or model. So it's a very similar idea, just it works on one higher level of this choosing between different models and using some measure to assess the quality of a model. Here we use a validation error to assess the quality of a hypothesis space, like the space of our linear predictors. And we can use this to say, okay, seems to be better than the space of degree 3 polynomials. So let's stick to degree 1 polynomials or linear predictors. Very good questions here. Let's see if I missed one. Yeah, then one question, how are the available data points partitioned into training and validation set? Yeah, as I said, we randomly select a subset as the training set and the rest is the validation set. And there I will then show in a few minutes, I will do a live demo where I show you with a few lines of Python code, which I cooked up half an hour before this lecture. And I'm not a pro in Python, I have to say. But they are so convenient libraries that all I talked about here, you can do in a few lines of Python code. Also this splitting into training and validation set. Okay. Yeah, so we now already discussed model selection. So model selection is done simply by looking at the smallest validation error. But there's another method, which is sometimes more convenient, which is called model regularization. So again, the training error, the average loss on the training set only guides the learning. We are not really interested in a small training error in practice. We are interested in getting a predictor which predicts well each new data point. We want to learn a predictor for Shazam that tells us the song title for each song recording that we record with our smartphone in any bar around Helsinki. Because sometimes they have good music, but you don't know the song. So you want this prediction to work well for any new data point. So in validation, in this validation approach, what we did in this regard was to probe the hypothesis outside the training set. So we used the training set. We used the training set to optimize the parameters or the shape of the curve. Here are degree 3 polynomials. And then we tried it out outside the training set. So we probe this degree 3 polynomial on a data point outside the training set. And then based on this probing gives us an estimate or an idea, what is the performance outside the training set. And there's another approach, which is quite clever, I have to say, and it took me a long time to really appreciate this, which is to estimate how the behavior changes. And this sounds a bit a mouthful, that it could be possible to estimate how the hypothesis would change its behavior outside the training set. How could we do this without probing the hypothesis on data points outside the training set? Well, and again, I must say, it's really useful to use some probabilistic model for the data points. And one such probabilistic model could be that the data points are so that the features are kind of wobbly. So any data point that we get, the features of the data point are subject to noise. So here the blue ones are actual data points that, for example, I read in from the Finnish Meteorological Institute. But the actual observed values, like in this case, the minimum daytime temperature, they are subject to some noise. So equally well, I could have observed this orange, this neighboring orange data points. So for each blue actual observed data point, I have some perturbed data points, which are equally reasonable. So which are equally reasonable to be occur at some point. And then what regularization does, it augments the training error. So this blue guy here, or this blue girl, is the sum over the training data points, the average loss over the training data points. This is the training error. And then we add a regularization term. So this here is called regularization term. And this regularization term is the hypothetical average loss that we would get when we also had these perturbed data points in our training set. And you can calculate this regularization term if you know the distribution. So if you have a probabilistic model for all these perturbed data points, and one such simple probabilistic model is just take each training data point and consider a whole ensemble of perturbed data points, which are obtained by adding some noise to the features of this blue data point. And we will work this out in round 4 in detail. You can write this down on pen and paper. What you would get, the training error, including these orange data points, and what you get is this regularized empirical risk minimization. So you get the original training error from the actual blue data points. These are the ones you get from FMI. And then you get another term, which is the training error that you would get additionally from these perturbed data points. Okay. Yeah, here I have worked this out in more detail. So we have these two components. And this second term, this regularization term, is again a design choice, because this regularization term, how this term looks in precisely, or what it is precisely, depends on which probabilistic model you assume for this perturbation. Is the perturbation only in the features, or is there also some perturbation in the labels a bit? And depending on these assumptions of these perturbation statistics, you get different regularization terms. Okay. Okay. I will not talk about more about regularization at this point. We will go into more detail in round 4. This was now meant to give you really the basic skills, the basic tools before you start heading out into your machine learning problem. So when you start training a model, always be aware of overfitting. So even when you get small training error, you might get a high validation error. And to find out this, you must do validation. I will show you now in a small notebook how this works. And another option, instead or as an alternative to model selection based on the validation error, you can do regularization. Okay, so let's now have a break of some 9 minutes and let's come back at 3:10 with a live demo about model validation. Yeah, you can ask questions on the chat in the meanwhile. Yeah, hello, back to the lecture on model validation, selection and regularization. So there were some questions coming up, which I'm going quickly over. One question was, what are the benefits for using regularization over validation? In regularization, you don't need to sacrifice data points for validation. So when you do validation, you always have to hold back some data which you cannot use for training the model. In regularization, you use all available data for training, and you kind of implicitly create more data points. So these perturbed data points that I showed you, these are in some sense artificially generated new data points. This is also called data augmentation. We will talk more about this in round 4. So when you have little data, regularization might have the benefit of not taking away or holding back data that you cannot use for training. In regularization, you can use all data points for training. And also in regularization, you can incorporate some knowledge that you might have about the data points in your particular application domain. So you might know, because you know about the hardware problems, that some features are more perturbed than others. And you can incorporate such knowledge, which is related to this probabilistic model behind this perturbed data points. You can translate such prior knowledge into regularization methods. So you can exploit this better in a more systematic fashion than with regularizations. With validation, sorry. Yeah, then another question, I'm still confused with regularization. Does it mean that you generate new training data points different from the original ones? Yes, so in some sense, regularization methods are based on augmenting the original data points by perturbed data points. But these regularization methods are not doing this explicitly. So there's no step where you start some random generator and produce perturbed data points, but you assume that you know the probabilistic distribution or the statistical sorry, distribution of these perturbed data points. And this distribution allows you to write down the regularization term. Sorry, I need to take a small break. So, excuse me. So you do not have explicitly to generate new data, but you need to know the statistical distribution of the new data. Yeah, there were several questions again on this grading of the machine learning assignment or the problem formulation. We will have a look into this with the TAs today and get back to you soon. Then another question, is it possible to have a live demonstration on how to practically select the value for the parameters that are design choices? For example, the regularization term. Yes, so I will ask TAs to prepare such live demonstrations. And as Professor Sick pointed out, actually next Wednesday, instead of a regular lecture, you will have also such a live demo for Python. Okay. So let me now switch my screen to the Jupyter Hub. So I cooked up a brief notebook to illustrate model validation and selection. First of all, I load in. So can everybody see my Jupyter Hub screen here? Yes, it seems so. Very good. So first I load in some data that I downloaded from the Finnish Methodological Institute and I store it as a CSV file. I load this data using a ready-made library called NumPy, which provides a function called load text, which reads in the columns of this file. And then I extract the second column, which has index 1 as the minimum daytime temperature, and the first column is the maximum daytime temperature. First thing I like to do is always to visualize data as a scatter plot. So we see here some 7 data points obtained from previous FMI measurements. So what do we do? Well, in machine learning, we try to learn a hypothesis. I start with a polynomial function. So the hypothesis is a polynomial function. And I learn the parameters of this polynomial function, or the weights using this function fit. So this function learns optimal hypothesis out of all polynomials. And we see that this, I can choose the maximum degree of the polynomial as 6 here. So if I would choose 1, which means a linear predictor, I would get this straight line here as the best fit. There's one question I couldn't find last Wednesday recording. We have put the link on the My Courses page. I will send it out again. And this demo will also be visible in the recording. Yes. So this degree here is a hyperparameter. We call this hyperparameter because it does not relate, or it does not belong to a single hypothesis, but this degree parameter chooses a whole hypothesis space. So if I choose degree 2, then I use the hypothesis space consisting of all degree 2 polynomials. And then this fit function searches the best hypothesis out in this space of all degree 2 polynomials. If I choose 3, then I use a different model, a larger model, all of degree 3 polynomials. And when I use degree 7, I get an even larger hypothesis space. And now the space is so large that the fit function finds one such hypothesis in this space. And one such hypothesis is a degree 7 polynomial that almost perfectly fits the training data points. But as we discussed earlier, this is no good in general, because if you look at this behavior, would you like this predictor? Let's see if I can zoom in here a bit. So this solid curve is a hypothesis that was learned by Python here. So this fit function, this dot fit function found this hypothesis, which reads in the feature, which is the minimum daytime temperature, and outputs the maximum daytime temperature. And this hypothesis perfectly fits, so it perfectly matches the training data. But is it any good? Is this hypothesis any good in your opinion? When you look at this plot? No, it's not. Why not? Yeah, there's one good comment. It would be quite something if the minimum daytime temperature is around -5, but the prediction for the maximum daytime temperature would be around +50. So this is highly unlikely that this happens in Finland. Yes, I will share this code with you. I will share this notebook with you for sure. So this is not good. And how can we find this out that it's not good without using our brains, without using our human intelligence? Well, machines need to do validation. And to this end, as I explained before in the slides, we split these 7 data points into 2 subsets. And we do this split using one single line of Python code, which is called train test split. So this validation set here is called test set. So this splits data into training and validation set. So we input this function, the arguments x, which is the features of all data points, and y, which is the labels of all data points. And it returns us 2 feature matrices, x train and x val, which is the features of the training set and the features of the validation set, and also the labels of the training set and the labels of the validation set. And using these 2 subsets now, we can compare the training with the validation error. So I now train this hypothesis, this degree 7 polynomial, only on the crosses, which is the training set. So I get training error 0, but a quite large validation error, 2.11. So, and what I recommend you, kind of some crude high-level advice, when you do machine learning, start with some powerful method like polynomial regression with degree 14 in this case. So try to get the training error to 0. So this would be a first step, a first milestone in your project. Try to get the training error 0, and then almost certainly you will overfit. And then you take it from here. Then you think about, how can I bring the validation error down? Yeah, one simple way is to reduce the model complexity or make the model smaller, like use a smaller degree here, a smaller polynomial degree. Let's see if it worked. Still, so 10 to the power minus 29 training error. So training error is essentially 0 up to numerical rounding errors, but the validation error large too. So it was not enough. So I go down more. Let's say degree 6. What do we get? Still training error 0, validation error almost 2. So let's do 3. Yeah, training error still 0, but validation error already going down. Validation error 0.14, but not enough. There's still a large discrepancy. Training error essentially 0, validation error not 0. So there's one question now. Isn't 0.14 not good enough? It might be good enough, but surely not in this case, because it's so much larger than the training error. This is what I do not want to see in the end of your reports. What I definitely want to see is at least one such comparison of training error and validation error. This is kind of mandatory. I want to see a discussion and a comparison of the training error and the validation error of whatever model you use. Okay, so it was not enough. Let's go down more. Let's make the model even smaller, degree 2 polynomials. Yeah, it's coming closer. 0.002 training error, but still at least one magnitude difference. So let's go down even more. Degree 1. Yes. Now we are at least in the same ballpark, but we cannot go down more, because then what we get will be degree 0 means a constant, and then the optimization doesn't work anymore. So degree 1 seems to be the best choice here. Yeah, there's one very good question. Seems like deciding the model is a manual process. Yes, quite often, always. At some point, it's a manual selection. There is no automated machine learning method, which you just tell what you want to predict, and it grabs the data, it chooses the right models from the beginning. It's just there are tools that help you to make this iterative procedure, which I just did, more convenient and more faster in some sense. Then another question, how much bigger the validation error can be compared to the training error? That's hard to say in general, but ideally it would be on the same level. So the training error would be within a few % of the validation error. Then another question, did the training error just decrease by decreasing the polynomial degree? Shouldn't the model choose 0 for high degree polynomials? So that the training error goes up. So what I did was I reduced the polynomial degree to bring down the validation error, but at the expense of the training error. So I intentionally increased the training error in order to get the validation error down. Then another very good question, could the difference be improved also with more data? Yes, absolutely. So what I did was reducing the size of the model. So choosing a different model, a smaller model. In this case, this meant using a smaller polynomial degree, but you could, alternatively, you can use more training data. So instead of making the model smaller, you can also choose to collect more training data points. This is also an option to bring down the validation error, but increase the training error. Yes, and it depends on the application. If collecting training data costs money, and there might be application where each training data point that you collect means that you have to call somebody, have to call a customer and ask him a question and maybe offer him something as a bonus to answer that question and to give feedback. So if it's so costly to collect more training data, it might be a better option to reduce the model complexity. But if it's possible to collect a lot of data and it's cheap, then you might also collect more data instead. There's another comment. Currently, the data points line up nicely, so a linear model makes sense. But if we add more data points, maybe a degree 2 polynomial makes more sense. Yes, so if we would add more training data points, then the trade-off would change. So adding more data points typically also increases the training error because it's more difficult to fit more training data points. So another question, where can I read about the functions used in the code example, lin space, predict, etc.? So you can find pretty good documentation by Googling. So if you Google just skikit learn, and the name of the function, like polynomial features, then you will pretty surely get some decent results. Another question, when fitting a linear model in machine learning, do you look at the traditional statistics metrics such as R2 or just go off the validation error? Well, this depends what metric you use. As I said, the loss function is a design choice. We could have also computed some other metric like R2, but I'm not sure for which applications that would be more suitable. So you can use different loss functions for computing the training error and the validation error. Here I choose to use the squared error loss, but you can also use other loss functions. Yes, so the validation error and the training error should be on the same level in general, yes. There was another question. So could we find the smallest difference between validation error and training error by looping over the degree? Yes, so that's what I did just. How come the training error was larger than the validation error in the example? I don't see yet where. The training error here is still smaller than the validation error. Yes, I do not understand now what this question referred to. Then another question, do we have to understand how the algorithm chooses the most optimal polynomial? No. So in this course, you do not need to understand how the details of these fit functions for any more complicated method. Maybe we'll look into details how this fit function works for linear regression. For linear regression, this amounts to solving a linear equation, so computing a matrix inverse. But other than that, we will mainly assume that we have some method to find the best hypothesis within a hypothesis space. Another question, is it important to compare the training to validation error? Isn't the validation error all that matters, since it simulates how well our model predicts labels? Yes, that's a good point. So as I said, we use this validation error as an estimate for how well it will predict or how well it will do on new data points on average. But what this is due to my research interests, I'm always interested in finding out, could I do better? And when you want to know if you already use the methods that you have optimally, you need to compare the validation with the training error, because when the training error is much smaller than the validation error, or still smaller, like here, then this might hint that there could be still some gains. You could do even better. But if you say a validation error of 0.06 is more than I ever hoped for, then you are pretty done. But then you might have soon a competitor. Imagine you develop an app which uses machine learning to predict customer preferences. The better you predict, the more customer you will make happy, and the more customers you will have. So you would miss the chance or the opportunity to do even better. And maybe some other company would try to harvest this potential gain that you have just by looking at comparing the training error with the validation error. That's why I will insist in the student project reports that you compare training with validation error. Another question, for our machine learning project, we need to create such a notebook? No. So you're not required to implement anything in a specific language. We just try to make Python attractive to you. But again, I promise you, and you can always rely on my promise, you don't need to be expert in Python coding or have had a course in Python coding. So we expect from you that you basically can use high-level interfaces for machine learning. And whenever you need a small piece of code, for example, to convert an image into a CSV file of RGB values, then reach out to the TAs, which will provide you such a small helper code. So you will not need to be a programmer in this course. You just need to be aware of the tools that are available and how to use them. Yeah, and I cooked up this demonstration here within 30 minutes before the course starts. And I never had a course on Python. I learned C++ 20 years ago. So you will be able to get along without being a Python programmer to do the machine learning project. And the report has to be in the form of a paper. So we do not ask you to submit Python notebooks or source code. You have to submit a report like you would submit at a conference. Yes, there's one comment. I had a hard time to access the Zoom link for the exercise sessions. Yeah, please send us an email and specify more detail what the problem was. We will try to improve the accessibility then. Another comment, the random selection of data points used for validation might remove some trends in the data set. Could it be better to choose points evenly divided over the whole scope of data points? Yes, so this random selection, this works only if the data points do not have an intrinsic order. One example of data points that are not of this type is a time series. So time series data, when you shuffle them, you kind of throw away structure in the data. In this course, we mostly look at data sets where the data points are just objects flying around and don't have any order. So we don't consider structures or orders in the data sets, like in time series where you have one data point followed by another data point, and close by data points in the time are more similar than far away data points. We don't look at such structures. This is something you look at in special topics of machine learning, like time series processing or computer vision, where the pixels of a data point or the pixels of an image, they are more similar if they are nearby than they are farther away. We don't use such relations or structure. That's why for such random data sets, we cannot destroy any structure because we assume they are random. But if you use if you look at time series data, then you must be more careful with how you randomly split into validation and training. But this is beyond the scope of this course. There's one question. Could you say something about the possibility of stratification if the data set is imbalanced? Yeah, so this is clearly beyond the scope of this course. So imbalanced data sets would refer to data points where, for example, you have only two different types of label values, like cats or dogs, and you would have 99.9% only cat images. Then you need to be careful that you reflect this imbalanced distribution also in the validation set, and that you do not use a validation set where all images are cats, then, for example. But yeah, these are already more advanced topics, which I want to leave out at this point. Okay. Yeah, I will share this notebook, of course. And please do not hesitate to ask questions. If you have questions regarding to this course book, also in the exercise sessions by email or on the Zulip discussion forum. And then, yeah, I would like just again to repeat my advice for the student projects. Just start doing, get your hands dirty as soon as possible. First, formulate the machine learning problem. You might use already the problem that you submitted in the first assignment, but you can also choose a different machine learning problem that might be arising in your studies, in your research, or everyday life. Then try to get some data, try to get some CSV files, some Excel sheets, try to get some data. And start with simple machine learning methods. Use a linear regression method and or polynomial regression. Try to get the training error to 0, which then, of course, might almost for sure result in overfitting. That means a large validation error, and then try out different methods to bring down the validation error, like regularization, using more training data, using different models, using simpler hypothesis spaces, like smaller degree polynomials, and so on and so forth. And then you iterate this model formulation, model evaluation, and then adaptation, and so on and so forth. We will provide more details on the review questions for the student projects as we go. So each one of you has then to review 5 other student project reports, and we will give you very precise criteria for these reviews. And of course, this criteria might also give you a good idea how your report should look like. And we try to finalize and release these review questions by next week. Okay. One other question, is there always a certain theme or subject that the TAs go over in the exercise sessions? For example, some demo. So should I attend some exercise session not to miss anything? Yeah, we generally ask the TAs to discuss the topics of the current round. So now we started round 2, regression. So they might show you demos how to do regression in in Python, how to do regression in Excel, how to do regression in IBM, SPSS, some drag and drop software. But the main purpose of these exercise sessions is to give you an opportunity to ask directly questions to the TA. And if the TA doesn't have an answer, he forwards the questions to us. Yeah, and the exercise sessions should be recorded. We try to record all the exercise sessions, so you will not miss anything if you cannot attend some of the exercise sessions. Another question, do you have tips on how to find a suitable problem for a project? It seems to me that there are endless interesting problems, but the main restriction is how to find a large, high-quality data set. Yes, so that's one challenge already, to think about where could you get data. So I mean, one interesting data set is, of course, the weather data by the Finnish Meteorological Institute, and you can use one and the same data and formulate many different machine learning problems. You could formulate a problem, predict if it will be plus or minus degrees in 3 days ahead. Or you could predict the maximum daytime temperature tomorrow based on everything you know today, and so on and so forth. So you can use this very same raw data and formulate the zillions of different machine learning problems. And you might also use the problems, the machine learning problems that you reviewed now in the first assignment to get inspiration. Yeah, just to emphasize, the student projects are solo projects, so there's no teamwork. And we will, of course, use different forms of plagiarism checks. And also the peer reviewers will be asked to check for plagiarism. Okay, that's all from my side for today. Then on Wednesday, you will hear about topics for round 2, which is about regression methods. Thanks a lot for your attention and see you soon. Bye.